Okay, problem number 1. The pharmacy at Metropolitan Hospital receives 12 requests for prescriptions each hour, Poisson distributed. So basically this part is reminding you that the demand arrival, is a random process which follows the characteristics of Poisson distribution. So here we can tell our lambda is what? 12 requests. Receives 12 requests per hour. So lambda is strictly provided as 12 per hour. Okay, per hour. And the inter-arrival time, which is 1 over lambda, is gonna be 1 over 12. So this is hour. So this is average time in between every arrivals. Okay, and I think next part is going to explain what's the service characteristics is like. It takes the staff a mean time of 4 minutes. Okay, so your service time, which is 1 over mu, is going to be 4 minutes, 4 over 60. So you have average service time, and from there you can actually get your mu, which is a service rate. So 1 over mu, which is 15 per hour. So if you really try to make sense of what's in here, it's basically telling you there are 12 customers arriving in each hour, and you can really serve 15 customers in each hour. So this is a time in between each pair of arrival, and this is really the amount of time you take to serve each customer. Of course, those are all average values. So first thing that with all the waiting line problems is that you need to determine which type of waiting line models you should be used to understand the solution. So we talk about 3 things: MM1, MMS, and MD1. So in this problem, it doesn't give you a lot to help you determine exactly which system is this. But I would just assume that this is going to be a MM1 because it doesn't tell anywhere. It says it has more than 1 server, more than 1 service station, or things like that. It doesn't really. Also, this is not MD1 because the service time is not constant. So MD1 is actually eliminated in the first place. And is this an MMS? It could be an MMS, but it doesn't really mention number of servers here. Therefore, I think it is very safe to use MM1 here. Yeah, that's a part of the most challenging thing with waiting line models. You need to determine what is the system before you start anything at this point. So the number of units in the system. Okay, so number of unit in the system, including the one currently being served, and number of people currently waiting in the line. So that's the number of units in the system. Okay, so where do you get it and how do you calculate those? So here, your PowerPoint slides. Also, the end of module D, it has a list of formulas for each waiting line models where you can use to find out the answers. Here, this is what it is: average number of units in the system. So, average number of unit in the system, right? So, this is actually what we need. I'm just gonna copy this to make our calculation easier. So we have formula we can take a look at as we do the calculation. In fact, I reminded everybody to make your Excel spreadsheet before the exam. Okay, you can develop a spreadsheet that's dedicated to the waiting line problems so that you can repeatedly use the Excel file whenever you encounter MMS problem. Okay, so it's basically lambda over mu minus lambda. So ls, the length of the system, is actually 4. So it's most likely, on average, there are 3 people waiting in the waiting line. On average, anytime. In general, there's 3 people waiting in the system, and 1 is actually getting served. That's why length of the system is 4. And the average time a prescription spent in the system. The average time a prescription spends in the system. Okay, so in this case, we're looking at WS, waiting time in the system. Okay, waiting time in the system. The moment it arrives to the waiting line, all the way until its service is finished and you're ready to depart from the pharmacy. So for this one is actually 1 over the difference between the mu and lambda. All right, so this is 1/3 of an hour. Okay, 1/3 of an hour. If you like to convert in a minute, you actually need to times 60. Okay, so that gives you 20 minutes. So this is a solution here. And the average number of prescriptions waiting in the system, average number of prescriptions waiting in the system. Okay, so I think earlier I mentioned something like it's most likely you'll see 1 people getting serviced and 3 people waiting in the system. Okay, so this part is gonna help us to find out more exact answer. So for that part, we need to move on to the next slide. So we saw this part, average number of units waiting in the system. Okay, so I'm just gonna screenshot this again. Go up. I'm gonna use that here. Okay, so it's going to be LQ. LQ is lambda squared. Lambda squared over mu times mu minus lambda, close parenthesis. So this is 3.2. So I think what this tells you is exactly in general exactly. Okay, but in general you see 3.2 people or 3.2 subscriptions waiting in the system. Okay, and then you see 0.8 prescription is getting serviced in the waiting line system. Okay, of course those are average numbers, so you can't exactly serve a fraction of a subscription, but this is just numerically telling us what's the condition of this specific waiting line system is like. Okay, so that's with the question number 1. Okay, let's move on to question number 2. This one is, let's just take a look at this thing together. I didn't really solve this in advance. I'm just kind of improvising it, like anyone would do, like any of you would do, seeing it and try to take time to think with you. Okay, so there are approximately 3 customers shopping in Fackert department store in Mexico City between 9 a.m. and 5 p.m. So I think I'm just going to quickly write down things I'm seeing. Total demand being 300. Okay, and daily service hour is going to be it looks like it's going to be 8 hours. Okay, and you have customers. And when deciding how many cash registers to keep open each Saturday, owner Susanna Fackert considers 2 factors. So customer waiting time and service cost of employees. So remember during the review week, I mentioned something like the total cost from a waiting line system can be categorized into 2 categories. Number 1 is the cost of maintaining the waiting line. It looks like this is it, the service cost of employee and additional checkout clerk. This is actually the cost that this Susanna will spend to maintain her waiting line. And customer waiting time, this part is actually will be measured in the form of a penalty, because the longer you make customers wait, the more you lose in several things, your good reputations, and sometimes people will leave because they don't want to wait long. Okay, so one is the cost of maintaining waiting line. The other is cost from a long waiting line, which is a penalty, sort of. Checkout clerks are paid an average of 4 per hour. So clerk wage is 4 per hour. $4 per hour, of course. When one is on duty, the waiting time per customer is about 10 minutes. Okay, so it doesn't look like it's a typical waiting line problem. Okay, you don't have to. I can sense that this is already giving you average waiting time each customer, which is your WQ part. You don't have to calculate it. This is actually providing it already. Okay, let's see further. When 2 clerks are on duty, average checkout time is 6 minutes per person. When 3 clerks are working, 4 minutes and 3 minutes with 4 clerks. So I'm a little puzzled about this checkout time, whether this indicates the service time or whether this basically means the same information presenting here, the waiting time per customer. So I think there's no way for us to infer the checkout time when there's 1 clerk when you're providing the checkout time with the 2 clerks. So at this point, I need to mindfully determine which direction I want to go. Okay, so the other direction where you consider this as the average service time will make this problem unsolvable. Okay, so what I'm gonna do is I'm gonna use this as the same information here, the customer waiting time. So this actually doesn't require you to do all these things. Okay, but you need to know at least when there's 1 clerk, your system is MM1. When there's more than 1 clerk, then your system is considered as MMS. Anyway, so from the way this question is presented, I think I can actually organize my spreadsheet something like this. So number of clerks. Wait a second. I'm just gonna move this to here. And we are evaluating we are evaluating 4 different waiting line system. Each system has different number of clerks. Okay, so 1, 2, 3, 4. So this is M1. Even though we don't need to do those sophisticated calculations, but I'm still expecting you to know how to determine what kind of waiting line system this is. Okay, so those are MMS because you have more than 1 server. So with this average waiting time is actually provided from the description. So when there's a 1, it's 10 minutes, which is 10 out of 60. Okay, 1/6 of an hour. When there are 2 clerks, waiting time is 6 out of 60. Okay, so 3, and there are 3, 4 minutes. Okay, 4 out of 60. And then where are 4 clerks? When there are 4 clerks, it's gonna be 3 out of 60. So this is decreasing. Okay, so this is decreasing, and which is good sign. But which scenario is gonna give him the least total cost? We need to calculate that. I think that's what the question is expecting, what the problem is expecting. So total waiting time for entire customers. Okay, so because it tells you that there are 300 customers coming during that period, so I'm just gonna multiply 300 here. Okay, so I'm gonna absolute reference it because in general everyone waits 10 minutes. Therefore, for 300 people, that's equivalent to 50 hours. Okay, cost of waiting. There must be some cost of waiting, right? Cost of waiting is how much? Yes, offers approximately $5 in lost sales and goodwill for every hour of customer time spent waiting in the checkout line. So that's $5, okay, per hour. So your cost of waiting for the first system is 50 multiplied by 5. Absolute referencing it again. Just double click to fill it. So as you can see that the pattern is the more clerks you're using, the less customers are waiting. Okay, I think that makes sense. And let's move on. What other costs we need to consider? It's the cost of wage. Okay, cost of wage. So when you have one employee that work for 8 hours, okay, each hour you're paying the person $4 per hour. Okay, so you're paying $32 when there are one clerk. Of course, it's going to double it, triple it, quadruple it. So this is the cost of compensations for each system. So that it's clear the total cost is going to be this plus this. Okay. Okay. So which system has the least total cost? Is my answer correct? Yeah, it looks like it's correct. Okay. So so before we move on, I'm gonna show you something interesting, something that I showed several times during the review week. So I'm just gonna highlight this. 4 different scenarios. There are cost components and total cost. Let's try to visualize this, okay? So as you can see that this scenario, the analysis is actually visualized, right? When number 3, 3 clerks are used, your total cost is the least here. Okay, so that's good. Okay, last question is question number 3. Okay, question number 3. So the Robert Oney's barbershop is a popular haircutting and styling salon near the campus of the University of New Havens. Why don't we say this is Winona State University? Okay. 4 barbers work full-time and spend an average of 15 minutes. So 4 barbers, whoa. 4 barbers work full-time and spend an average of 15 minutes. So 4 barbers. So you have it looks like we're dealing with an MMS system, okay? MMS system. So number of server we have here is 4. And an average 15 minutes on each customer. So your 1 over mu is actually 15 over 60. Am I right? Yes, 15 minutes out of 60 minutes, which is an hour, is a quarter hour per customer. So quarter hour per customer. That means in each hour you're serving 4 customers. All right. And the customer arrive all day long means you're dealing with an infinite population, infinite demand pattern at an average rate of 12 per hour. An average rate of 12 per hour. So your lambda here, your lambda is 12 per hour, and your inter-arrival time is 1 over 12. Okay, whatever that is. So if you want to know what's the minute, I'm just curious. You do 60 here. Okay. Oh, in every 5 minutes. Yeah, that makes sense. Every 5 minutes, you see 1 customer walk in. In every hour, you see 12 customers walk in. All right. Arrivals tend to follow the Poisson distribution. Again, this is indicating your arrival is a random process. Service time is also a random process. Oh, I hate this description, negative. This makes it so difficult to understand. But it's the same thing, okay? The software described in this quantitative module may be used to answer the following questions. Again, this is MMS system, right? If you remember from the sample final exam I distributed, I actually didn't. Yeah, this is the this is the formula you ought to use. But I actually did not. Instead of letting you use this, I actually provided a website. Okay, we're gonna use that website again to answer this particular problem. Okay, website is here. Some of you mentioned that this is not opening from your computer. So in that case, you may try a different web browser like Edge or Firefox. If you don't have those, or it still doesn't work there, you can try to use your cell phone. Okay, so we select the model, we select this, and we have 4 server, and our lambda is, what was our lambda? Our lambda was 12, and our mu was 4. Okay, so let's do it again. Oops. Okay, so let's calculate. So it's gonna start to give us some answers here. So probability that the shop is empty is, okay, probability that shop is empty. That's a probability of 0 people in the system. Okay, probability of 0 people in the system. Therefore, the answer is this one, P0. P0, 0 people in the system. Okay, I can say, oops, P0 is equal to. And the average number of customer in the barbershop is average number of customers in the barbershop. This average number of units in the system, right? Those who are getting serviced and those who are currently waiting altogether. So let's see here, number customers in the system, which is 4.5283. And the average time spent in the shop is average time spent in the shop. So this is actually, okay, let me, average number of customers in the barbershop, this is the length of the system, okay? And this is going to be waiting time in the system, which is here, WS, average time spent in the system. And what else? Average time that a customer waits to be called to the barber chair. Basically this is about the average waiting time, okay, which is waiting time in the queue. The average, which is here, okay, which is here. An average number waiting to be serviced. Average number waiting to be serviced, which is length of the queue, okay, waiting number of people currently waiting here. And so the robber is thinking of adding a 5th barber. Oh, this is gonna give it a huge twist to the problem. Adding a 5th barber. I mean, this is a huge twist if you're not using the software, okay? So instead of 4, this is looking for utilization, which is our role, right? Which is our role is what. So currently when there are 4 servers, your utilization rate is 75%. And when this is a 5, let's give a little time. So this is actually the utilization per server, but this is asking the utilization of his shop. Okay, his shop. So it's not here, where do you get the answer? So I think we do this. 1 minus P0. P0 is the probability that there are 0 people in the system where everybody is idle. Okay, but as long as there are 1 person getting serviced, that means your shop is being utilized. Okay, so 1 minus P0 in return will tell us what is the percentage of time that this shop is busy. Okay, which if you look at P0, it's 0.466. Okay, 1 minus 466. Okay, therefore this will become the answer. Okay, so yeah, we confused a little bit earlier, but I think that's a very good learning process we had. So at least now you know we need to distinguish the difference between the utilization of each server and the utilization of the entire system. This is asking utilization of the entire system. This is utilization of a single server. It doesn't have this directly, but you need to calculate it by reading this probability. Okay, so how do you read this again? Each bar here represents the discrete probability, which is probability of exactly one person, two people, three people, four people in the system. Where this curve here is the cumulative probability, where this is telling you that the probability of 3 or less in the system, 4 or less in the system, 5 or less in the system. Okay, not to confuse this with 1 or less in the waiting line. It's not 1 or less in the waiting line. This probability is about the number of people waiting currently in the system. Okay, so that's the difference. So, okay, that kind of concludes all the problems with the waiting line. Hope this helped a little bit with your review on this part.